Hi, this is Dr. John Bergduff. In this video, we're going to look at the future value of an annuity, but in particular, we're going to look at how we can use the formula to determine payments. So I'm going to jump to the example first of all, so you can see what I'm talking about. Example 1, you believe the value of the stock market will increase at a rate of 6% per year, and you use this rate to plan your retirement at age 65. You want to retire with $2 million. How much should you invest per month if you start investing at age 30? So this is a classic example of a problem involving the future value of an annuity. You're going to be making periodic payments once a month with the goal of reaching a certain future value in the when you retire, in this case. The formula can be used as is. Many books will say that if what you want to calculate the payment, you need a separate formula. And I don't think we need to do that. Let me take a look and see if we can figure this out. So the quantity we do not know is the payment. We do know what amount or future value we eventually want to reach. We want that to be $2 million. We do know what we believe the interest rate is going to be over this period of time. And we have to convert that to a decimal. 6% is 0.06. We're going to be making monthly payments. So N, which stands for the number of payments per year, should be 12. And the time, if you begin investing at age 30 and retire at age 65, that's an expanse of 35 years. Now, if you notice the quantity that's unknown is on the right side of the equation. What we can do is we can calculate the quantity that's multiplied by P on the right side of the equation by calculating this value, the quantity 1 plus r over n raised to the power n times t minus 1, all divided by the quantity r over n. And once we have that, we can solve for p. So let's take a look. Let's use our graphing calculator and calculate 1 plus r over n to the nt minus 1 divided by r over n. First of all, we're going to open a parentheses, and actually we need to open two parentheses. We're going to say 1 plus, the r is 0.06, divided by n, which is 12. That quantity is raised to the power n times t. To raise a quantity to a power, you use this button. It looks like a little hat that actually represents a caret. In the newer brands of calculators, you'll see this looking like an exponent, and you'll just enter the exponent. In the older versions of the TI calculators, you would have to put this in parentheses. Let's use parentheses in our exponent anyway, just to be sure. It's a pretty good practice. N times t, so n is 12, t is 35. I need to then get out of the exponent, and I do that by clicking this right arrow here on this circular wheel, minus 1, close the parentheses to close out everything you see besides the p in the numerator. All of this is divided by the quantity r, 0.06, divided by n, and n again is 12. And we'll go ahead and hit enter, and this is what we're going to get. Now, I'm not going to write that number down, but just to see where we stand at the moment, the calculation we are trying to do at the moment is hunting for the value of p. And this is where we are right now. We know that our A is 2 million. And we have P multiplied by this number we just calculated, which I'm just going to write down a couple decimal places of just to take a look at it. So you can see that if I want to find P itself, what I'll need to do is I'll need to take 2 million and divide by this number that I've just calculated. Now I could just write down every decimal point, just write the number down, but an easier thing to do by far is to take this number that I've calculated, store it into memory. I do that by clicking the STO button here, followed by a memory location. The simplest one is to use the XT theta N button here. Hit enter, and this quantity has now been stored into the calculator as the value X. So when I need to calculate 2 million divided by 1424.71, all I really have to do is say, what is 2 million divided by X, the quantity that's stored in memory. And then this gives me precisely the value for P that I need to know. Round that off to the nearest cent. And what that tells me is that my monthly investment, if I want to raise this much money, would be $1,403.79. Now, actually, since the 79 cents is just ever so slightly below what it would be if you actually invested 79 cents, $1,403.79, you would probably come up just a little short. So a lot of folks would say, well, just to be safe, let's change that to $1,403.80. Yes, technically that should round down to 79 cents, but if we make it 80, we know we'll actually just barely go above $2 million, and we won't have to worry about some small amount when we're done. $1,403.80. As another example, let's do the exact same problem, except ask ourselves the question, what if we started investing not at age 30, but at age 45? Here's a couple of things that would change. Your A, your R, and your N would all be the same. That would all be the same, but T would change. You're now going to start investing at age 45 with the goal of retiring at age 65. That means your number of years is now 20. Let's see what's different. If I go to the same set of calculation, just change 20, change 30, the 35 I had before to 20. Let's do it this way. Open a parentheses, open another parentheses. 1 plus 0.06 divided by N. Notice that so far none of this is dependent on T. Raise that to the power. This will change. N is still 12, but T is now 20. Get out of the exponent by using the right arrow key. Minus 1, close parentheses, divided by what's in the denominator, which is going to again be 0.06 divided by 12. That calculation will give us this number. So the calculation we now are looking at is going to be, what is the solution to the equation? 2 million equals P times 462.04. And you can see that to solve that, you would need to take 2 million and divide by this number, 462.04. But again, let's not just write that down. Let's store that into the memory. Like before, store into X and hit return. And to do the calculation that I need, I'm simply going to take 2 million and divide that by X, which will have the value 462.04 stored in it. Hit enter, and we'll get a new payment. Now, see, look here, you see the payment that would be necessary per month would be $4,328. And let's do the same trick. Let's make that 63 cents so that we're sure that we have enough. And I want to notice the difference in these two numbers. This is the power of compounding. If you start at age 30, you would need to put away $1,403.80 per month. But if you don't start till age 48 and you want to reach the same goal, that payment skyrockets to $4,328.63 per month. So, obvious moral of the story, if you're working on planning for retirement, start early. Thank you very much.